Welcome back. Problem 7-46. So statement is the beam is subjected to shear of 800 Newton. Determine the average shear stress developed in the nail alongside A and B. If nails are spaced 100 millimeter apart, each nail has a diameter of 2 millimeter. So you can see this is the beam, and that is made up of these wood that are nailed together at side A as well as at side B. These nails are spaced of 100 millimeter and having diameter of 2 millimeter, and a shear of 800 Newton is applied. So you have to find the average shear stress developed in this nail. So let's start with the solution. We know that shear flow is equal to horizontal shear force per unit length, which is the space, and that shear flow is also equal to V into Q divided by I. So what we do is that we have this V, we do not have Q, we do not have I. So we'll find first I, which is section property. So for section property I, which is not known, so we will first find the neutral axis passes through centroid. So because this beam is not symmetrical about a horizontal axis, so we will first find the centroidal axis passing centroidal axis. So for that we have formula, which is y bar is equal to sum of y dash y into y dash into a divided by sum of area. So let this is 1 and this is 2. Since A board and B are same, so we will write it y dash 1 y1 dash into A1 plus 2 times y2 dash into A2 divided by A1 plus 2 times A2. Now what is y1 dash? So if we take this upper surface as a reference line, so this is 1, so this area will be A1. So y dash will be equal to A1. A1 is, you can see, 250 millimeter multiplied by 30 millimeter. Clear? So 250 millimeter in term of meter is 0.250 multiplied by its thickness, which is 30 millimeter, and 30 millimeter is 0.03. What is y dash? So y1 dash, so y1 dash is distance from the top surface till the mid of this first. This distance is y1 dash, and this y1 dash is 30 divided by 2, which is equal to 15 millimeter. So 15 millimeter is 0.015 plus 2 times A2. Now A2 is this area, which is 30 multiplied by 115 millimeter. So 115 is 0.150 multiplied by 30 is 0.03 into y2 dash. So y2 dash is distance from top surface till the mid of this seconds. This distance is y2 dash, and this y2 dash is 150 divided by 2, which is equal to 150 divided by 2, which is equal to 75 millimeter, and 75 is 0.075 meter, divide by area A1. A1 area was 0.250 multiplied by 0.03 plus 2 times area 2, which is 0.150 multiplied by 0.03. So when you calculate it, you will get y dash, the location of neutral axis passing through centroid, is equal to 0.04773 meter, or you can say it is 47.73 millimeter. What does it mean? It means that from the top, the neutral axis or centroidal axis passing through its neutral axis, centroidal axis will be this one. So this distance from the top, this is your y dash, y bar, which is equal to 47.73 millimeter. Now you have I. So by using parallel axis theorem, we will find I, which is I is equal to sum of I dash plus AD square. So for first one, we will have 1 over 2, 1 over 12. I am talking about this one. So we'll first find the moment of inertia of this, which is equal to 1 over 12, its breadth, into h cube. H is 30 millimeter. So I will write 1 over 2, 0.250 in meter, into h is 0.03 whole cube, plus area. Area is again this 0.250 into 0.03 into d square. Now what is d square? So distance from neutral axis till the mid of this section. So this is your d1. This is your d1. So d1, you can see that it can be obtained if you subtract y1 dash from this. Clear? So y dash in meter is 0.04773 minus y1 dash is 0.015 whole square, plus 2 times 1 over 12. Now we will calculate the moment of inertia for this. So its breadth is 30 millimeter and height is 150 millimeter. So 1 over 12, breadth is 0.03 into height is 0.150 whole cube, plus area, which is equal to 0.03 into 0.150 into d square. Now what is d square? So d square is distance from neutral axis till the mid of second section. So this is the mid of second section and this is the neutral axis. So this distance is d2. So I will write this distance is d2, and this can be obtained if you subtract y dash from this y2. You can see that if you subtract this distance from this distance, clear? So you will left with this. So this distance y2 dash is again that was y2 dash was 0.075 minus y dash, which is 0.04773 whole square. So when you calculate it, you will get the moment of inertia for the beam shown above is 32.164 into 10 raised to the power minus 6 meter power 4. Now you have this I, you have V, you do not have Q. So what we will find Q? We know that Q is equal to y dash bar into A. So you can see that here this is the shaded portion. This one is the shaded portion in which we use this nail to connect with this. So this is the area A dash. So this is A dash, and y bar is distance from neutral axis till the mid of this section, which is this D1, and D1 was this one. D1, this value, this one. So I will write it 0.04773 minus 0.015 into area. Area is 250 millimeter, which is 0.250 multiplied by 0.03. So when you calculate it, you will get Q is equal to 0.245 into 10 raised to power minus 3 cubic meter. Now you have V as well, so you can just put it in this formula. Q is equal to shear flow, which is horizontal shear force per unit length, is equal to V into Q divided by I. So V is equal to 800 pound. Q is 0.245 into 10 raised to power minus 3 divided by I, which is equal to 32.164 into 10 raised to power minus 6. So from here you will get the value of shear flow is 6105.4 Newton per meter. Okay. This 800 is not in pound, this is in Newton. So kindly make this correction. So now we have shear flow. We know that shear flow is also equal to horizontal shear force per unit length. So you can just put the value of Q 6105.4 is equal to FH divided by S. S is the spacing, nail spacing, which is 100 millimeter. So 100 millimeter in term of meter is 0.1. So from here you will get horizontal shear force will be equal to 0.1 multiplied by 6105.4, and we will get horizontal shear force will be equal to 610.54 Newton. Now this I will write it, since each side of the beam resists this shear force, then average shearing stress in the nail will be equal to FH divided by 2 into area. You can see that you have nail on this side as well as on these sides. Clear? So the shear force will be divided by 2. So that's why FH divided by 2 into area. So FH is 610.54 divided by 2 multiplied by diameter of nail is given. So area is pi by 4 into 2 millimeter. In meter it is 0.002 whole square. So when you calculate, you will get the average shearing stress in the nail comes out to be 97.2 megapascal, which is the answer of this question. And that was all about this problem 7-46. I hope you have enjoyed this video. Those who are new to my channel, then I will request them to subscribe it, and don't forget to press the bell icon. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-18. So this problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by RC Hibbeler. And the statement of the problem is the bolt shank is subjected to tension of 80 pounds. Determine the resultant internal loading acting on the cross section at point C. So you can see we have been given that the bolt is subjected to 80 pounds in tension. So we have to find the internal loading at point C, at cross section at point C. So this will be normal force, there will be a shear force VC, and we have moments. All these are internal loading. So let's start with the solution. So first step is that if you cut this at point C and draw the free body diagram. So first I will draw the free body diagram. It will be like this. Okay, then we have like this. So this is your point C, where you have a normal force when you cut it, clear, and this normal force will be NC. There will be a shear force which will be VC, and there will be a moment, reaction moment, MC. We have been given that in this shank of the bolt we have a tension, so the force that is exerted by this bolt on this portion will be in this direction, clear, and this will be 80 pounds. So this force will be 80 pounds. Also, from point C till this, the radius is given as 6. So this distance from this till the mid of this, we have this distance is 6 inch. Now we will apply equation of equilibrium in order to find this MC, NC and VC. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see only horizontal force is NC. So I will write this is in plus direction. So NC, and the second force that is 80 pounds in positive direction. Their sum must be equal to 0. So from here you will get NC is equal to minus 80 pound. So our answer is negative. It means that we have assumed this direction NC is toward right hand side, which is negative. So I will write, so our assumed direction is wrong and NC should be towards left hand side. Okay, but the magnitude of NC is 80 pound. Now we'll find VC by using another equation of equilibrium, and that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So here you can see only the vertical force is VC, which is acting downward, and there is no other vertical force. So I will write minus VC is equal to 0. It means that VC, there is no vertical shear force acting on this at this point. Now the third load is that we will use the third equation of equilibrium is that sum of all moment about point C is equal to 0, taking the counterclockwise moment as positive. So about point C, these force NC and VC are not producing any moment because these are passing through this point. We have a reaction moment which is MC, that is counterclockwise. So I will write MC, and the moment that is produced due to this 80 pound force into perpendicular distance at about point C is 6. So 8 into 6, and this is also producing counterclockwise moment, so it will be positive. So I will write plus 80 into 6 is equal to 0. So from here you will get this MC will be equal to minus 480, and the unit will be in pounds into inch. So this is the reaction moment, and we can see that this moment comes out to be negative. So it means that our assumed direction of MC is wrong, and it should be in clockwise direction. To keep equilibrium. To keep it in equilibrium. And this was all about this problem 1-18. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-25 that is taken from chapter number 4, Axial Load, and the book name is Mechanics of Material by RC Hibbeler. Statement is determine the elongation of A36 steel member when it is subjected to axial force of 30 kilonewton. The member is 10 millimeter thick. Use the result of problem 4-24. So you can see this is the 836 steel member that is acted upon by a tensile load of 30 kilonewton, and the thickness of this member is 10 millimeter. This width is 20 millimeter and this width is 75 millimeter. So you have to find the elongation with the help of results of problem 4-24. So let's start with the solution. So first we will write given data. So we have been given that this is A36 steel member clear, and that is subjected to axial load which is equal to P, and that P is equal to 30 kilo Newton. Thickness T is given as 10 millimeter, and this 10 millimeter in meter is 0.01 meter. Now you can see this smaller width which is taken as D1, and that D1 is equal to 20 millimeter. In meter it is equal to 0.02 meter, and this width, which is the largest width, that is taken as D2, and this D2 is equal to 75 millimeter, and that is equal to 0.075 meter. Also you can see that this is the height of half of the portion, and this height is taken as 0.5 meter. So it is also given that use the result of problem 4-24. So we will take the results from that which we have solved in previous problem. So what we have to find is determine the elongation. Determine the elongation. So let's start its solution. So if we move to the previous problem 4-24 which we have solved, I have attached the link in this problem. So this is the result. So you have to copy this, and this result which we will write it over here, this deformation which is delta is equal to P into H divided by E into T into D2 minus D1 into ln of D2 over D1. So first let me clear it. You can see that this was the problem. This is the smallest width D1 and this was the largest width D2, and that is acted upon by a tensile load, and total height is H. So for that, deformation comes out to be this one. So you are aware. Now you can see this is the half portion. So if I add other half like this, so this problem will be exactly the same like this one. You can see this is half and this is half, so total will be this one. So for that, our total elongation in this case will be equal to 2 times of delta. So you can put the value 2 into PH divided by E, that is steel member. So we will write E steel into thickness D2 minus D1 into ln of D2 over D1. So you have all the value. You can see you have P, you have T, you have D1, D2, H. You do not have E, and E for steel member. So E for steel can be obtained from the book and we will move toward the book. Is if you go at the end of the book to the properties table below, so you can see the second last one is average mechanical property. So if you click at that, and you can see that this is A36 steel, so its E is 200 gigapascal. So note down this value is equal to 200 gigapascal. So 200, and that will be equal to 200 into 10 raised to power 9 Pascal. Now you have all the values, you can just put it. So you will get elongation, our total elongation will be equal to 2 multiplied by P is 30 kilonewton. So 30 into 10 raised to power 3, H is 0.5 meter. All the values is given over here. You have to just put the value. E of steel is 200 into 10 raised to power 9. Thickness is 0.01 and D2 is 0.075 minus D1 is 0.02 into log of 0.075 divided by 0.02. So when you solve this, you will get this elongation, total elongation. I will write total as well. So total elongation will be equal to 0.360 into 10 raised to power minus 3, or that will be equal to 0.360 millimeter. So that will be total elongation. And this is the answer of our this question number 4-25. And that was all about this problem. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 9-40, and that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by RC Hibbeler. So statement is the wide flange beam is subjected to 50 kilonewton force. Determine the principal stress in the beam at point A located on the web at the bottom of upper flange. Although it is not very accurate, use the shear formula to calculate the shear stress. So you can see this is a cantilever beam that is acted upon by a 50 kilonewton force at this end, and the cross section of this beam is shown, that is I beam, clear. And from here you can see this is the flange, these two are flanges, clear, and this is what we call web. So you have been asked to find the principal stresses in the beam located on the web at the bottom of, this is the top of the flange and this is the bottom of the upper flange, and this is upper flange and this one is lower flange. So you have to find the principal stresses at this point A. So let's start with this solution. So first step is that we first find the state of stress at point A. So for that, if I cut this beam at point A and draw the free body diagram, so this is the beam, clear. This is point where there is a point load X, and that point load is 50 kilonewton. That this length is 3 meter. Okay, and when you cut it at this point, so there will be a shear force that will be acting upward. which is represented as V, and there will be a moment that is equal to M. Clear? So we will find this shear force V and moment M. So for shear force, we will apply sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So we can see V is acting upward and 50 kilonewton is acting downward. Their sum must be equal to 0. So it means that shear force is equal to 50 kilonewton. And the moment can be obtained by using equation sum of all moments. Let this was your 1 point, about point 1 is equal to 0, and taking the counterclockwise movement as positive. So you can see about point 1, this shear force is passing through it, so it is not producing movement. So this force is producing movement, and the perpendicular distance is this 3 meter, and this is clockwise, so it will be negative. The second movement about point 1 is this counterclockwise movement, which is the reaction movement. So their sum must be equal to 0. So M, which is counterclockwise positive, minus 50 into perpendicular distance 3 is equal to 0. So from here we will get this movement will be equal to 150 kilonewton into meter. Now here you can see that we have a shear force V acting, and we have external moment M acting. Clear? So let this is the x-axis. Clear? This is y-axis, and this z-axis is out of plane. So your this movement is about z-axis. Clear? So due to this, you will have a stress, bending stress in x direction. So I will choose another color. You will have a bending stress in x direction, and this shear force will be along y direction. So if I draw the state of stress, clear, but before we will have sigma x, clear, which is not known yet, and we have a shear force which is given as 50 kilonewton. So we will calculate shear stress, which we also do not know. So what we will do, we will find this sigma x, and we know that this sigma x is equal to m into y divided by I, where m is the bending moment, which we have calculated over here. Y is distance from neutral axis till topmost. So if you see that this is the beam, so it's symmetrical about this axis. Clear? So y is the distance from neutral axis till the point where point A lies. So this is the distance. This distance is y. And this distance, you can see it is equal to 250 millimeter divided by 2, which is equal to 125 millimeter. And this y is in term of meter is 0.125 meter. Now we have y as well. I can be obtained by I is the second moment of inertia, and for this I beam it is equal to, if we take this hole as 200 by this total length is 250 plus 12, which is equal to 274. So this is 274 millimeter, while width is 200 millimeter. So if I take this whole box and find the moment of inertia and then subtract these two empty portion, so we will get the moment of inertia of this beam. So I will write moment of inertia is equal to, generally it is equal to 1 over 12 bh cube. So for here I will be equal to 1 over 12. B is its breadth, which is 200 millimeter, and meter it is equal to 0.2, and height is 274, so which is in meter is 0.274 whole cube, minus 1 over 12 into, you can see this height will be equal to 250, and this will be equal to 200 minus 10 divided by 2, which is equal to 95. So 95. So I will write its breadth is equal to 0.95, and height is 0.250 whole cube. And there are two empty portion. One is this one and other is this one. So I will multiply it with 2. So So I will multiply it with 2. So it will be equal to 2 divided by 12. Clear? So when you calculate it, you will get the moment of inertia, and this I will be equal to 95.4512 into 10 raised to power minus 6 meter power 4. Now you have all these things, so you can find this sigma x. So sigma x is equal to moment, which is equal to 150 kilonewton. So kilonewton will be converted into newton into meter. Y is 0.125, clear, divide by I, which is equal to 95.45123 into 10 raised to power minus 6. So you will get sigma x will be equal to sigma x will be equal to 196.43 megapascal. And this stress is at point A. So we will get this is also equal to sigma A because it is calculated at this point A. Y is taken from neutral axis till point A. Okay. So we have sigma A is equal to 196.43 megapascal. Now we'll find shear stress. So we know that shearing stress is equal to V into Q divided by I into T. So for point A, it will be equal to shearing stress at point A will be equal to V into QA divided by I into T. So what is the Q? So you can see that we will find, since this point is here, so the above the point A, this area will be taken, and we know that QA is equal to Y dash bar into A dash. So A dash is this area which I am going to shade. So this area is A dash. Its width is 200 millimeter and thickness is 12 millimeter. So first I will calculate A dash. A dash is equal to thickness, which is 0.012, clear, and width is 0.20 meter, which is 200 millimeter, clear. And Y dash will be equal to distance from neutral axis till the mid of this section, clear. So this is Y dash. This is equal to Y dash bar, and this is equal to this distance, which is 0.125, and the half of this 12 millimeter. So it will be equal to this distance is 125 millimeter, 125 millimeter plus 6 millimeter. So it will be 131 millimeter Y dash bar, and that is 0.131 meter. Okay, now you have the value, put it, Y bar is 0.131 meter. So your QA will be equal to 0.131 multiplied by this area 0.012 into 0.200. So when you calculate it, you will get QA will be equal to 0.3144 into 10 raised to power minus 3 meter power cubic meter. Okay, now we have QAV is given as 50 kilonewton, which we have calculated at point A. We have QA I is also known this, and thickness. So this is the thickness. You can see this point A, and this thickness is 10 millimeter, which is 0.01. So thickness is equal to 10 millimeter, or it is equal to 0.010 meter. So you have all the value, put the value V is equal to 50 kilonewton. So 50 into 10 raised to power 3. Q is calculated as 0.3144 into 10 raised to power minus 3. I, which we have calculated, was 95.4512 into 10 raised to power minus 6, and thickness is 0.01. So when you calculate it, you will get shear stress at point A comes out to be 16.47 megapascal. Okay. So you can see this is the shear stress. Now we have here two stresses. One is normal stress in x direction, which is sigma A, and other one is shear stress, which is TA. So if you represent it on a state of stress, let's say this is an element at point A. So your normal stress, which is sigma A, is this one, clear, and your shear stress is TA, clear, and shear stress is TA. Okay, so if you represent this TA, so it will be like this. This is your shear stress on this face, which is equal to TA. There is no normal stress in y direction, so it will be 0. So from here you can see that you have sigma x is equal to sigma A, and that is equal to 196.43 megapascal, clear. Sigma y, which is not available, and that is 0, and tau of xy is equal to shear stress at point A, which is equal to 16.47 megapascal. Okay, now we know that principal stress is sigma 1 comma 2 is equal to sigma 1 sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So just put the value. Sigma x is 196.43 plus 0 divided by 2 plus minus 196.43 minus 0 divided by 2 whole square plus 16.47 whole square, which is equal to sigma 1 comma 2. So again sigma 1 will be equal to 196.43 divided by 2 plus 196.43 divided by 2 whole square plus 16.47 whole square. And when you calculate it, you will get it 198 megapascal. Similarly, you can calculate sigma 2, and sigma 2 will be equal to 196.43 divided by 2 minus under the root 196.43 divided by 2 whole square plus 16.47 whole square. And when you calculate it, you will get minus 1.37 megapascal. So at the end, we have calculated the principal stresses, which are the maximum stresses at point A, is equal to 198 megapascal, and other principal stress is minus 1.37 megapascal. And that was all about this problem 9-40. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Also try problem 9-41, that is exactly same, but here the principal stresses will be at point B. So try it, and my next video will be about 9-41. Thank you. Welcome back. In our previous video, we solved problem 9-40, and in this video, we are going to solve problem 9-41, that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by RC Hibbeler. So statement is the wide flange beam is subjected to 50 kilonewton load. Determine the principal stresses in the beam at point. Now here it is given that point B located on the web at the top of the bottom flange. So you can see this is the cantilever beam that is acted upon by 50 kilonewton load at this end, and the cross section of this beam is shown, that is I beam. So you have to find the principal stresses at the point B located on the web at the top of the bottom flange. So you can see this is bottom flange, this is top flange, This is web, so you have to find the principal stresses at point B. Clear? That is sigma 1 and sigma 2. So let's start with the solution. So first step is that we are going to find out the state of stress at point A. So for that we will cut the beam at point B or at this section AA. Clear? And draw the free body diagram. So it will be like this. Clear? This is point where you have a point load of 50 kilonewton. Clear? This length which is given as 3 meter. So when you cut it at section AA, clear, this is section AA. So you will be having a shear force in upward direction which is equal to V, and you will be having a moment like this. So we will find this moment and shear force. So for shear force we will apply the sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So two forces, one is V and 50 is acting. So V is upward, so it will be positive, minus 50 is downward. Their sum must be equal to 0. So it means that this shear force is equal to 50 kilonewton. Now we'll find this moment. So for moment we'll apply sum of all moment about section AA must be equal to 0, taking the counterclockwise moment as positive. So about this section AA, the one moment is due to this 50 kilonewton load into perpendicular distance is 3, and this is producing clockwise, so it will be negative. The second moment is this external moment which is counterclockwise, so it will be positive. So their sum must be equal to 0. So I will write m minus 50 into 3 is equal to 0. So from here this moment will be equal to 150 kilonewton into meter. Now you can see that here we have one shear force that is acting upward, clear, which is V, and we have a movement which is counterclockwise. So due to this movement, this is x-axis, this is its y-axis, clear, and this is the z-axis. So you can see this movement will be about z-axis, this movement, and the shear force that is acting downward will be in y direction. So due to this movement, the normal stress will be generated, or bending stress will be generated in this x direction, which is sigma x. Clear? So we'll find this sigma x, and due to this shear force, we will be having a shear force. So what we will do is that we will find this sigma x, which is generally we are calculating at B, and due to shear force V, we will have shear stress. And since we are finding at B, so we will find this. So we know that sigma x, or sigma at point B, bending stress due to bending moment, is equal to moment into y divided by I. Clear? So moment is 150 kilonewton into meter. So what is y? So y is again this symmetrical beam. If you take the mid axis of this beam, so y is distance from neutral axis till this point B. This is equal to y, and this y is downward, so it will be negative, and it will be equal to minus 250 divided by 2, which is equal to minus 0.125 meter. It will be equal to 125 millimeter. So in meter it will be equal to this one. And what about I? So we will find I, which is section property, and that is equal to 1 over 12 BH cube. So B is this 200 and H is equal to this total is 274. So we will take this whole box and we will find the moment of inertia about this axis, and then we will subtract the moment of inertia of this remaining two. So it will give you the moment of inertia of this shaded portion. So 1 over 2, B is 200 millimeter, which is in meter is 0.200, and height is 274, which is 0.274, minus 2 times 1 over 12 B is equal to 95. You can see this is 200, so 200 minus 10 will be equal to 190, and 190 divided by 2 is 95 millimeter, which is 0.095. Okay. And height is 250, so it is equal to 0.250 whole cube. Now when you solve this, you will get the moment of inertia comes out to be 95.45123 into 10 raised to power minus 6 meter power 4. Now you have all the values. You can find sigma b is equal to m into yb divided by I. So moment is given as 150 kilonewton. So 150 into 10 raised to power 3 yb is minus 0.125. Clear? Divide by I, which is 95.45123 into 10 raised to power minus 6. So when you solve this, you will get this sigma b comes out to be minus 196.43 megapascal. So this is the normal stress or bending stress due to bending moment. Now we will find the shear stress at point B, which is equal to V QB divided by I into T. So we have shear force V is given as 50 kilonewton. Clear? I is again we have calculated 95.45123 into 10 raised to power minus 6. T is equal to, you can see this is the thickness. Let me show you, this is point B. So thickness is 10 millimeter, and this 10 millimeter is equal to 0.010 meter. And what about QB? So QB will be equal to Y dash bar into A. And what is Y dash bar and what is A? So A is this area. This is the A. And this area is equal to 200 millimeter, which is 0.2 into thickness is 12 millimeter, which is 0.012. Clear? And what is Y dash bar? So Y dash bar is distance from neutral axis till the mid of this section. This is Y dash bar. And that is equal to, this distance is 125 plus this 12 divided by 2 is 6. So 125 plus 6 is equal to 131 millimeter. And this Y dash bar in meter is 0.131 meter. So I will write Y dash bar is 0.131 meter and A dash is 0.200 into thickness is 0.012. Okay. That is equal to QB. And when you solve this, this will be equal to 0.3144 into 10 raised to power minus 3 cubic meter. Now you have all the values, you can just put it, so you will get shear stress at point B is equal to shear force, which is 50 kilonewton, so 50 into 10 raised to power 3 multiplied by QB is 0.3144 into 10 raised to power minus 3 divided by I, which is 95.45123 into 10 raised to power minus 6 into T is 0.010. So when you calculate it, you will get shearing stress at point B comes out to be 16.47 megapascal. Okay. Now, if we draw the state of stress at point B, so let this is state of stress. This is the element. Clear? So you will having a in x direction you will have sigma b is negative, so it will be compressive. Clear? This is sigma b, which you can see that is minus 196.43, and you will be having a shear stress which is 16.47, so it will be like this. This is shearing stress at point B. Similarly, over this face it will be downward and this will be like this. Now you can see you have sigma x here is equal to sigma b, which is equal to minus 196.43 megapascal. Sigma y here is not available, so it will be equal to 0. And tau of xy, which is equal to shear stress at point B, is equal to 16.47 megapascal. Now principal stresses, we have to calculate principal stresses, and these principal stresses are the maximum stresses, which is equal to sigma 1 and sigma 2. And we know that sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Now just put the value sigma 1 comma 2 is equal to minus 196.43 plus 0 divided by 2 plus minus under the root minus 196.43 minus 0 divided by 2 whole square plus 16.47 whole square, and all these are under the root. So for sigma 1 is equal to, it will be equal to minus 196.43 divided by 2 plus this 196.43 divided by 2 whole square plus 16.47 whole square. And when you calculate, it will be equal to 1.37 megapascal. Similarly, you can find sigma 2, which is equal to minus 196.43 divided by 2 minus 196.43 divided by 2 whole square plus 16.47 whole square under the root. And when you calculate it, it will be equal to minus 198 megapascal. So according to this, sigma 1 is 1.37 megapascal and sigma 2 is equal to minus 198 megapascal. So these are the principal stresses that is acting at point B due to the given loading. And that was all about this problem 9-41. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-21. This problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by RC Hibbeler. So statement of problem is the forced steel clamp exert a force of 900 Newton on the wooden block. Determine the resultant internal loading acting on section AA passing through point A. So you can see this is a forged steel clamp and that exert 900 pounds on this wooden block. This is wooden block. You have to find the resultant internal loading at section AA passing through point A. So it means at point A you have to find the normal force, shear force and moment. So let's start with the solution. So first step is that when you cut this clamp at section AA and draw the free body diagram. So first of all I will draw the free body diagram. So this is the clamp portion. So here you can see you have like this curve form. So let's draw it like this. Okay. This is section AA. Clear? This is section AA. And this section AA makes an angle of 30 degree with this horizontal. This is your point A. Clear? Now when you cut it, so you will be having a normal force acting on this surface which is equal to NAA. Clear? You will be having a shear force on this face which will be equal to VAA, and you will be having a moment which will be MAA. Now you can see that this clamp exert force of 900 Newton on this wooden block. As a result, the wooden block will exert 900 Newton force in upward direction on this clamp. Also, the distance between this point A and this application of this force is 200 millimeter. So this distance is 200 millimeter. Now we will take this x-axis, this will be as x dash axis, and this will be y dash axis, because your this normal force and shear force exert along this axis. So we'll find the internal loading by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x dash direction must be equal to 0, and force in this direction is taken as positive. So you can see this is the 900 Newton force that act perpendicular to this surface. So if I extend this line, if I draw a line that is at 30 degree with the horizontal, and this 900 will have two components. One is this component which is equal to we will talk, and the second one is this component. Clear? So what will be this angle? This angle. So you can see this is 30, this will be 60 degree, so this will be also 30 degree. So this component will be equal to 900 into cos of 30 degree, and this component will be 900 into sine of 30 degree. So we will apply equation of equilibrium. So first equation of equilibrium is sum of all forces along x direction must be equal to 0. So one force along x dash direction is this one, which is VAA dash, and this is toward positive. We have taken this direction as positive, this direction. So this will be negative. And the second force is this one, which is 900 into sine of 30. So their sum must be equal to 0. So I will write minus VAA plus 900 into sine of 30 will be equal to 0. So from here you will get VAA, which is the shear force, and this will be equal to 450 Newton. Now we will find this NAA, and we will use the equation of equilibrium is that sum of all forces along y dash direction must be equal to 0, and force in this direction is taken as positive. So you can see this force NAA is in positive direction. Clear? And this component is in negative direction as per our understanding or assumed direction. So their sum must be equal to 0. So I will write NAA minus 900 into cos of 30 degree is equal to 0. So from here NAA will be equal to 900 into cos of 30 degree, and that will be equal to 779 Newton. So you have NAA as well. We will find this moment MAA. So we will apply equation of equilibrium that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, one moment is MA, which is clockwise, so it will be negative. The second moment about point A will be this load 900 into perpendicular distance is 200 millimeter, and this is producing counterclockwise, so it will be positive. So I will write minus MAA plus 900 into 200 millimeter, and 200 millimeter in meter is 0.2 meter. So from here you will get MAA will be equal to 900 into 0.2, which is equal to 180 and unit will be Newton into meter. So all these are the internal loading at point A, and that is the answer of our this question. And that was all about this problem 1-21. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Also leave your comment about this video. Thank you very much. Welcome back. Problem 1-41. So this problem is taken from chapter number 1, that is stress or internal loading, and the book name is Mechanics of Material by RC Hibbeler. So statement is, if average normal stress in each of 20 millimeter diameter bar is not allowed to exceed 150 megapascal, determine the maximum force P that can be applied to joint C. So you can see this is a truss A, B, C, and each of this bar of the diameter is 20 millimeter, and allowable stress should not exceed 150 megapascal. So you have to find this maximum load P that can be applied to joint C. So average normal stress in each of the bar should not exceed 150 megapascal, that is 150 into 10 raised to the power 6 Pascal, and diameter of each rod AB, BC and CA is 20 millimeter, that is 0.020 millimeter, and we have to find the maximum force P at joint C. So let's start with the solution. So from this truss, you can see it is a right angle triangle. So we have to find this angle theta. Clear? So we know that AC is given as 1.5 meter and AB is given as 2 meter. So we'll find this AC. So AC is not known. So by using Pythagoras theorem, we know that AC square is equal to, sorry, AC, this is BC, not AC. So BC square is equal to AC square plus AB square. So you can just put the value, AC is 1.5 square plus AB is 2 square, and we take the square root on both sides, will give you length of BC. So from here you will get this BC will be equal to 2.5 meter. Now you have this BC. So what we will do is that we will take joint C as C, and we will analyze it by method of joint. So you can see, due to this load P, it will cause the compression in AB. As a result, the load applied by this BC on point C will be like this. And similarly, due to this load P, it will move, this AC will move toward this side, causing extension or tension. As a result, the load applied by AC at joint C will be this one. So let me draw this joint C. So this is a point C where you have a load of P that is acting in this direction, and this is the load BC at this point. This is load BC, and this load BC will be in this direction. Let this load is FBC, and at point C the load due to FAC or AC will be like this. Let this is FAC. Here this FBC will make an angle theta. So we'll find this theta, and we know that tangent of theta is equal to here this perpendicular, which is AC, divided by this hypotenuse, which is BC. So I will write AC over BC. The length of AC is 1.5, length of BC is 2.5. So from here we will get theta is equal to tangent inverse 1.5 divided by 2.5. And when you calculate it, you will get this theta will be equal to 36.86 degree. Now you have this theta, so you can see that we will apply equation of equilibrium for finding this FAB and FAC. So first equation of equilibrium is that sum of all forces in the x direction must be equal to 0 and force in this direction is taken as positive. So horizontally there is a force P applied, and the second one is the F horizontal component of FBC, which is FBCX component, and that will be equal to FBC into cos of theta. Clear? So I will write plus P minus FBC cos theta, that is equal to 0. So P is there, P minus FBC, we are interested to find of FBC, so FBC will be equal to P divided by cos of theta. And when you put the value of theta, P divided by cos of 36.86, so when you calculate it, 1 divided by cos of theta will give you 1.25. So FBC is equal to 1.25 times P. Now you have this FBC, we will find this FAC by using another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force that is acting vertically is this minus FAC because it is downward, and another one is this vertical component of FBC, which is equal to FBC sine of theta. So I will write minus FAC plus FBC into sine of theta is equal to 0. So we have to find FAC. So FAC will be equal to FBC sine of theta, and sine of theta is 36.86 degree. Okay. So we know now FBC, which is 1.25 times P. So FAC is equal to 1.25 times P multiplied by sine of 36.86 degree, and you will get FAC is equal to 0.75 times P. So I will write FAC is equal to 0.75 times P. Now you can see that initially I have told you that this member is in compression FAB, clear, and this member will be in tension. So we will write it over here. I will choose another color. This is in FBC is in compression, so I will write C, and AC is in tension. Okay. Now we'll move toward another page. We will find this FAB. So for that we will take this joint B and we will apply method of joint. Okay. So take point B and apply method of joint. Okay, so here at point B you can see that you have a reaction force that is due to this roller support at point B. This is By. Due to this member BC, there is a force which is in this direction FBC, and this makes angle theta with horizontal, and there is a load due to this member FAB. So the load will be like this one. So we will draw it over here. So this is point B. This is your point B. Here you have a load due to reaction load which is By, clear. On horizontally there is FAB which is in this direction, and load due to FBC is like this, and this makes an angle theta. This is FBC. So we will find this FA by using equation of equilibrium, and that is sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So horizontally we have this FAB in this direction which is negative, and the other one is this horizontal component of this, and this horizontal component is FBC into cos of theta. Their sum must be equal to 0. So I will write minus FAB plus FBC into cos of theta is equal to 0. We are interested to find out FAB. So FAB is equal to FBC into cos of theta. FBC, which we have calculated, is 1.25p. So 1.25 times p, and cos theta is 36.86. So when you calculate it, you will get this FAB is equal to P. And again you can see that this load is on joint B is like this. So as a result, this load will be the load in stress in member AB is in tension. Okay. So I will write this as tension T. Now you have FBC, which was 1.25 times P. You have FAC, which is 0.75 times P, and FAB. FAB is equal to P. So we have to find the maximum P at joint C. So for maximum loading, average normal, let me write it, average normal stress. Since the cross-sectional area and allowable normal stress of each bar are the same, member BC having maximum normal force. You can see that this member is a maximum 1.25 times P. So maximum normal force is the critical member. So critical member. So we will find this P based on this average normal stress. We know that average normal stress allowable is equal to FBC, because this is the maximum divided by area. These two values are same, so we will get FBC is equal to allowable into area, and area for circular rod or bar is equal to pi by 4 d square, and d is 20 millimeter or 0.02 meter square. So you will get area is 0.3142 into 10 raised to power minus 3 square meter. Now this FBC is equal to 1.25 into P is equal to allowable stress. Allowable stress is 150 into 10 raised to power 6 psi. So 150 into 10 raised to power 6, and area is 0.3142 into 10 raised to power minus 3. And when you calculate it, you will get P will be equal to 150 into 10 raised to power 6 into 0.3142 into 10 raised to power minus 3 divided by 1.25. And you will get this load P will be equal to 37.699 Newton, or this P is equal to 37.7 kilo Newton, which is the answer of this question. And that was all about this problem 1-41. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-42. This problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by RC Hibbeler. So statement is, determine the average shear stress developed in pin A of the truss. A horizontal force of P 40 kN is applied to joint C. Each pin has a diameter of 25 mm and is subjected to double shear. So you can see this is the truss. At point C we have a load of P, and at point A we have a pin support, and at point B we have a roller support. At A we have pin support. So you can see this is the side view, and there is a pin which is double shear. So we have to find the average shear stress developed in the pin. So let's start with the solution. So first step is that if you remove this support at point B, so you will be having a reaction force which is represented as By, and if you remove this pin support at point A, so you will be having a vertical force in downward direction which is Ay, and there will be a horizontal force in negative x direction which is Ax. So we'll find this Ay, Ax and By by using internal loading. So I will write internal loading. We will apply equation of equilibrium in order to find these stresses or forces. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, these two forces Ay and Ax are not producing movement because they are passing through it. So first movement that is produced by this By into perpendicular distance is 2 about point A will be in counterclockwise direction, so it will be positive. The second movement about point A is due to this P load, and perpendicular distance is 1.5 and it is producing clockwise, so it will be negative. And the sum of these two movements will be equal to 0 about point A. So I will write By into 2 minus P into 1.5 is equal to 0. So 2By minus P is given as 40. So 40 into 1.5 is equal to 0. So we will get 2By will be equal to 40 into 1.5. And when you calculate it, you will get By will be equal to 30 kilo Newton. Now you have this By, so we will move and we will find Ax and Ay. So for finding Ax, we will apply this equation of equilibrium, that sum of all forces along horizontal must be equal to 0 and force in this direction is taken as positive. So you can see this force which is Ax is negative, plus this Py which is in this positive direction is P. So their sum must be equal to 0. So minus Ax plus P is equal to 0. So from here Ax will be equal to P, and we know that the value of P is 40 kilonewton, so Ax is equal to 40 kilonewton. Now you have this Ax as well, and we will find Ay by using in third equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So we have two forces, one is this one minus Ay and plus By, their sum must be equal to 0. So I will write minus Ay plus By is equal to 0. So Ay is equal to by, and by is equal to 30 kilonewton. Now you can see we have all these three reaction forces. So you can see that uh, at point A, so if we find the reaction forces of these two, so this will be equal to A force, and this A force will be equal to, or we can also write FA. So this FA, by using Pythagoras theorem, net force at A, net force at A will be equal to FA, and that will be equal to AX square plus AY square under the root. So just put the value. AX is 40, so 40 square plus AY is 30, so 30 square. So from here, when you calculate it, you will get FA will be equal to 50 kilonewton. Now this 50 kilonewton acts on this uh, uh, pin support at point A. So you can see that we have been given that the pin is, each pin has a diameter of 25 millimeter and is subjected to double shear. It means that if you draw the pin like this, clear? So the net force that is acting on this pin is in this direction, or the direction of this will be in this direction. Why? Because two are both in negative direction. So this force will be equal to FA. So due to double shear, there will be a shear force VA in this direction as well as in this direction. So VA. So by using equation of equilibrium, that this shear force VA will be equal to F divided by FA divided by 2 due to symmetry. So 50 divided by 2 is equal to 25 kilonewton. Why? Because we have double shear. Okay, now you have this shear force, so we will move and we will find the average shear stress. So I will write average shear stress, which is equal to tau, and that is equal to shear force VA divided by shearing area. So how we will find shearing area? So diameter of pin is given, so shearing area will be this one, and this diameter is given 25 millimeter, which in meter is 0.025 meter. So area is of circular shape, or circular pin is pi by 4 d square. So put the value pi by 4 into 0.025 power 4 will give you 0.4909 into 10 raised to power minus 3 square meter. Now you have V, you have shear stress, so you can just put over here that average shearing stress is equal to VA divided by shearing area. Clear? So VA is 25 kilonewton. So 25 into 10 raised to power 3 Newton divided by shearing area is 0.4909 into 10 raised to power minus 3. And that will give you 50.9 into 10 raised to power 6 Pascal. And when you convert it into megapascal, so it will be 50.9 megapascal. And this is the answer of our this question. So the average shear stress developed in pin at point A is 50.9 megapascal. And that was all about this problem 1-4. 42. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.